Hello. Today we'll talk about illumination. So these are the today class objectives. We will talk about how we can consider the light information during rendering models. So this includes how we can actually specify light sources, also what are the illumination models. Also the last time we talked about how we can perform this triangle rasterization using edge equations. Also we talked about the technique for parameter interpolations like the color interpolations. I also one of the some of your questions also that one of your fellow students asked this question. So basically, there will represent the different types of model, including the complex ones with some of these triangles, right? But he or she thinks that actually this using too many triangles obviously not a good idea. For example, it might be very inefficient to split the sphere into triangles and also to apply this rasterization for each of these triangles. I agree upon your idea, but actually this is even though even though it is very inefficient for human, it could be the efficient for the machine. That's that's the main difference. The how we actually how we do the operations, also how the machine do their operations. So also actually I know that actually there are many different techniques how we can represent different types of the models, including this kind of this sphere. So obviously the representing these every little ones manually with triangle is very complicated. So that's why actually there are these kinds of the subdivision meshes. Actually, this the kind of the camera clock surfaces. This is actually the main mesh actually can be represented by the sum of the triangles, but actually there are certain rule. In other words, there are certain rules that we can subdivide this kind of rectangular shape or triangular shape into the more finer set of triangle. Also, there are actually non-linear representation of the basically these vertices of the triangle or quad can be the control point, and based on those control points, we can define this kind of the non-linear shapes like the sphere. But actually, we actually in the end in the computer in the modern GPU, we actually we are certain rule that transform this kind of control point or a set of triangle quad that actually have they're having this kind of control point into by applying this kind of subdivision rule, we can actually reach this kind of very smooth nonlinear one. This is actually known as the camera clock surfaces. I cannot talk about these little details, but actually in theory, these camera clock surfaces can provide infinite resolution for achieving this kind of smooth surface. So to do that, actually, this indicating that actually we are having some sort of continuous mathematical representation, but we actually representing that kind of continuous one, even this kind of discrete representation with a triangle. Also, I didn't really talk about the little details of this rendering pipeline, but but once we specify the vertex, actually there are some of these operations actually corresponding to this kind of vertex processing. Over there, actually we can have the different types of the algorithm like this vertex shader, tessellation algorithm, also this geometry shader. With this tessellation and also this geometry shader, we can subdivide. We can actually implement these camera clock surfaces, and then we can actually represent we can actually compute the very fine level of the triangle that even represent this kind of smooth surface like this sphere. Also, the long time ago, this Ed Camel, who is one of the main developer of these camera clock surfaces, actually become this one of the main leader behind the Pixar Studio. Also, actually, they received this Turing Award about 2020. Also, they used these camera clock surfaces to represent this kind of the very smooth to represent this kind of the virtual character with this smooth set of triangle. But behind it, they're actually using these camera clock surfaces. I didn't really talk about the little details, but if you're interested, you can check it out. Also, in my lab, also we work on we work on the ray tracing of this kind of some of these kind of smooth surface that are represented by the camera clock surfaces. So if you're interested, you can also check it out this paper. But actually, I didn't give the right answer actually to the question. But actually, the one of the main message is that even though some operations very dumb to the human being, but it could be the very efficient for other machines or even the AI, since actually the machine and humans are different. Okay, so now let's get back to our main material about our lecture. So basically, we didn't really talk about this. We didn't really talk about this question. How can we see the object, right? Think about how can you see the object. So in the end, it actually boils down to this kind of emission of the reflection of the light and material interactions. Also, there are light, right? We know the light, but actually this light is nothing but a subclass of the electromagnetic waves. You know that actually there are only the very small narrow band of this frequency. This is actually visible, the rainbow color. We can see only those regions within this kind of the wave, electromagnetic wave that have this kind of wavelengths. And we know that actually, if we run through, if we pass through the sunlight through the prism, actually, it can actually decompose into these different the ray, the electromagnetic waves that are having these different wavelengths. We know that. And also our eye, right? We actually cornea, and then actually we receiving the light energy, the light energy from here to there, and then also we actually this kind of the beam of the ray, light ray, actually the focus on this kind of the retina, where actually we have this kind of photoreceptor, where this kind of, you might heard about this the rod and cone. Cones actually usually corresponding to the RGB kind of RGB. Also, cone also they're more sensitive to this light intensity. But in the end, in the physics, we know that the electromagnetic wave, but there's no concept of the red, green, blue. But how we perceive that, actually happen in our brain. Actually, human brain actually basically human brain receive receive this kind of the rod, this kind of response from the different types of cone, but these cones actually having the different sensitivity. For example, human actually in some type of cone, I will say this blue cone actually have the high sensitivity at a particular this wavelength, but actually we perceive it as actually blue, but also there are some other types of cone which actually have the high sensitivity on this kind of wavelength, which actually we call it the red one. So human actually had these three different types of cone, but actually birds have evolved in a different way. So actually they have the different types of cone that are corresponding to the other types of the frequency. So somehow we actually the red, green, blue cone correspond actually give the different the behavior according to the different wavelengths, and then our brain perceive this kind of active level from the different types of cone, and then we actually we make the illusion that they are actually this kind of color. But one thing, basically that's actually a rough overview how we perceive from how we can see object from the light through our eye, also some of the retina and cells, also how we can actually, I briefly talk about how we can actually perceive those colors in our brain. But also there are lots of actually theory and the story about it. If you're interested, you can check it out. But that's why actually in the end, I'd like to point out that there's no reality about the color. That's actually our illusion, how we perceive about the universe. But even though we actually observe that one, that's not the reality. Also, now let's talk about there are some other there's a light and material interactions, right? Actually, sun emitting a lot of the energy with the different wavelengths, right? So everything's mixed together with a different frequency. So that's why it actually looks like this white light. But if the white light intersect with this kind of leaves, but this actually looks like green, right? Mainly because it actually reflect the kind of the light that actually the certain energy that actually have the particular wavelengths that are corresponding to the green. That's why it looks like the green. but also in the end, the leaf material absorbs the light other than the green light. So that's the kind of intuitive explanation, but everything can be explained by this electromagnetic wave. So here, some of the energy actually reflects from the leaf. That's why the reflection, or some of the energy actually absorbed here. Also, here the emitting actually, basically sun actually emit the energy. Also, there are some light source in our this light bulb also emit the energy, right? So emission and reflection, one of the key things that we need to consider further to actually answer the how can you see the object also in terms of the rendering. But actually, that's what will happen in reality. But so far I talked about the rasterization, but we didn't really basically if you recall the rasterization process, those process does not match with that. So in other words, there are lots of gap between the rasterization process and also what actually happened in real life. So also I don't want to talk about the details how we can actually perceive the mirror or the white paper. Think about it. I mean, you are now seeing this kind of if you look at the white paper, actually in every angle we can see that we can perceive the white paper. How can it possible? How can we see that that kind of the white paper from any other directions? Think about it. Now let's talk about the details about the illumination models. Also, actually, in the end, we wanted to mimic what really happened in reality. Along that direction, actually, we are having this kind of physically based illumination model. This kind of the technique models, this kind of the techniques actually based on actual physics of light interaction with the matter. But actually, a lot of the prior technique developed in the computer graphics is a later empirical models. It's a simple model that approximate object phenomenon. We mainly using this kind of empirical model since this kind of simple also that's why actually we can actually compute this kind of illumination model in an efficient way. But due to thanks to lots of this advancement of the GPU, we can use the physically based approach, even though it kind of require lots of these computations. So there are two components of illumination model. Typically, whatever model we are using, typically there are two components. One is actually light sources, also the other one is actually surface, this material property. Light sources actually typically we can represent this kind of light sources. There's some kind of light here, right? We actually we need to specify what are the actual emitton spectrum. I mean, what are the actually frequency that the light energy with what kind of the frequency. But typically we call it just the color RGB channel. Also, this kind of this geometric shape of the light sources. Also, each positional direction, or how much actually also the energy can be attenuate. So it might have some sort of this directional attenuate factor. There could be many other factors, but these are some examples. Also, there are material properties like this reflectance spectrum. Also, basically the blackboard actually reflect the energy small, but actually some of the metal-like the material actually reflect a lot of energy, right? Also, when you look at the material, it has certain color, right? That basically basically depending on the material property, we call it this reflectance spectrum. Also, it actually it defines each look, the color of the material. Also, the surface itself has its own geometry, position, orientation, other ones. Also, this absorption property. But actually, here when you define this kind of material, typically we actually using this kind of function BRDF, bidirectional reflectance distribution function. It describes the transport actually basically describe transport from the incoming energy to the outgoing energy. Typically, this outgoing energy also the radiance. I cannot talk about basically this. I don't want to give you the actual mathematical definition of the radiance, but you can just treat it just the energy. Here, basically, suppose that actually we are having some sort of material here, but this material actually we are actually more we are actually interested to know about what are the actually how we look like depending on the light source, right? Suppose that we actually having the light source at that direction. This is actually we call it this pi I. this is given the incoming incoming light direction. Also, there are basically the viewer can be located here. Then, how much energy we receive from that direction? I mean, the suppose that you are actually receiving this energy in that direction. Then the question is that how much energy it can reflect along that direction. I mean, basically we put our eye here. So then I want to compute the color, and then that color actually physically saying that that's a radiance. That's actually radiance. So we need to measure the radiance. Given how much energy we received, how much energy we can, how much energy this much to reflect along that direction. That's the outgoing outgoing light direction. In this case, we actually use this pi r. So basically, there are this actually there are two direction, incoming, outgoing direction. This is actually bi-directional. Also, this also how much it describes how much energy this material actually reflects. So basically, there also it explains how much energy actually distribute along this kind of outgoing light direction. That's why it actually we call it this BRDF, bi-directional reflectance distribution function. Also, there's another reason why we have we call this bi-directional. So here actually we actually consider this incoming light direction, also outgoing direction. But under the BRDF, actually we assume that even though we are getting the light energy at that direction, also it reflects the same amount of energy from that direction. So it actually the kind of the reciprocal. We actually assume some sort of the reciprocal property. But anyway, so basically BRDF is actually one of very common the concept that is describing the material actual appearance. How can you measure the BRDF? Actually, there are a lot of research going on how we can effectively, also in a cheap way, to measure this materials the BRDF. This kind of device typically called gonio reflector. Basically, it's a 4D. I didn't really talk about why it's a 4D, but given the incoming direction, we can actually use the two. There are actually to define this incoming light direction. It is actually we need to use these two different parameters. So two parameters for the incoming light direction. Another for the outgoing direction. Also, we need to use another two parameters. So that's why it's the 4. So it's the 4D measurement. So given the light direction, outgoing direction, then we actually emit the energy from that direction. Also, we capture this light energy, the reflect energy by locating the camera. Also, we can change this angle of the camera, also light. So that's why actually we need to have this kind of device. Of course, actually, it takes a lot of time since actually we are measuring we need to explore this 4-dimensional space. And in the end, if we actually represent this BRDF, we can use it for render this kind of the model, this kind of geometrical shapes with a different material. It's a nickel, also this gold paint. But basically if you are actually BRDF actually 4-dimensional function. Also if we can actually use it, I mean a lot of recent techniques also using this BRDF. But a lot of the prior techniques actually it was difficult to actually directly use the BRDF since mainly it is actually very slow. So a lot of simplification has been made by the computer graphics systems. So these are some of the examples. So we typically compute the only direct illumination from the emitters to the reflector of the scene. What do we mean by the direct illumination? Let me change it to the pen. So here, this is light source here. It actually this is our eye. So basically direct is that this light source interact the light source emitting the energy in that direction. Also it intersect with here at that location, and also this material reflect the energy to our eye. Then we can see that, right? This is actually the direct illumination. Indirect illumination is that basically there's another one here, another material, and then there's a hitting there, but instead of reaching our eye, also it actually reflecting there, one more bounce, right? And then we call this indirect, and then it ends up there, right? Also, there could be many other there are actually many ways of actually emitting the energy from there, hitting there, hitting there, hitting there, hitting there, right? There are a lot of the many bounds, right? But those then, other than only one bounce, we call it this direct, or all the other ray paths having the more than one bounce, we call it indirect. Let's get back to the laser pointer. And then also another assumption is that, another simplification is that we ignore the geometry of light emitter. I mean, some case we need to consider the light emitter, but typically actually we actually just we actually assuming very simple one for the light emitter. For the reflector, actually for the reflector, obviously the geometrical the material we actually consider this geometry of the reflector, which is typically represented by the triangle. Now actually I'd like to talk about the common empirical illumination models. So actually in the end it will be actually this phone illumination model, but actually phone illumination model has a different terms. But I'd like to talk about actually this ambient light source, the concept of this ambient light source. The ambient light source is kind of simple hack for the indirect illumination. And basically for this one, actually, we are just using incoming ambient illumination, which is nothing but just constant for all surfaces in the scene. So basically, ambient light source is just constant vector for everywhere. And then here, actually, we are using just RGB color here. For this object, we're using this kind of blue color. For all other one, this kind of one. This actually just constant color. Early on, actually, when I first came to this concept, it was very difficult to understand it. But actually, this is just the drastic simplification here. So basically, before I talked about given this light source and then these materials, just in the scene, actually there could be a lot of basically a lot of these bounds, right? Then in the end, at that case, actually we receiving that one through our eye. So obviously the long time ago, even today, actually simulating this kind of many bounds with the ray tracing or some other one takes a lot of time. Actually, right now we are talking about the rasterization, but later on, basically we will talk about ray tracing algorithm. But actually, they're simulating this kind of the ray interaction between the light interaction between light and material takes a lot of time. So we cannot consider this one. So there's no way that we can consider this one. So that's why early on, so they just drastically approximate this one as your ambient light source, which is nothing but just constant factor. Obviously, it's a very drastic drastic simplification, but back then we didn't have solutions, so we're just using this one. So the reflected ambient illumination, we call it ambient light source, just constant light source. Reflected ambient, the ambient is indicating the background illumination. This one, basically there's to constitute indirect light, there actually some sort of the light source. This one, this actual light, that's the intensity of the light source. Also, each individual material, also there are actually the reflector, also constant reflector. Here, that's why I used R here. R is actually indicating the illumination of the light source. Reflected ambient illumination depends on only the surface ambient reflection coefficient, the Ka, not the position and orientation. This is a drastic one. So in the end, to compute this, the RA, the ambient term of the reflected energy, that illumination, governed by the incoming the light source, which is actually only give us the light intensity, I of the IA here, the illumination of the ambient light source, and then we just modulate it with this kind of the material dependent the surface ambient reflection coefficient Ka. So in the end, just this is just constant. This quantity typically specified RGB channel. So that's why actually we can have this kind of color here. But obviously the ambient light source also that's just constant. That's the drastic simplification for the indirect illumination. But when you think about it, is the direct illumination, which accounts for the high portions of this light energy. So point light source is nothing but basically we assume that there are point light source like this, and then this light source emit the light energy from a single point into any kind of directions. Also, there's a simple approximation to the local light source, such as the light bulb. But the question is that suppose actually this actually represented by the triangle, and then we actually at that cases we actually rasterizing, and then at that case we need to compute the color. We need to compute the color. We need to consider how much energy we can receive from the light source to there, right? And then to do that, we need to consider these light directions. Light direction very basically like this. This the light direction actually vector from the p dot to the pl dot here, and then basically this is the vector. Also, typically we actually normalize it. So like here I use the hat here. This actually normalized of that vector from this location to there, and then basically you can see that since actually this direction to the light source change across the surface, right? So since this light direction can change, also if obviously you can feel that actually some of this color maybe they're changing across the surface, right? I will get back to that issue how we can consider this the light vector L. Also, there are directional light source. I mean, if you look at the sunlight, it doesn't change. I mean, it doesn't change the direction, right? So basically light some of the sunlight actually the parallel and have no origin, so it can be considered as actually point light at infinity. So even though you are moving on the surface, actually the light direction doesn't change. It's mainly because that the location of the light source very far away from the viewer, right? It's a very good approximation for the light source, just vector. Again, the direction to the light source is actually constant over the surface. And then the question is, how can you specify point and the direction of light? Can you guess? Actually, basically, we are just using the actual homogeneous coordinate for I cannot get back to the price slide when I recording with the PowerPoint slide. So here, further the light direction. Let me change the pointer. For the directional one, this is actually vector, right? So we can see that actually this kind of the 1, 1, let's say 1, and then the 0, right? This is actually indicating vector, right? So that actually we can represent it as this one. Well, the point light source we can obviously using the 1, 1, 1, like the 1, right? And indicating the point, right? So we can use the homogeneous coordinate to indicating the point light source, also the directional light source. Also, there are some of this kind of spotlight. This is actually a point source whose intensity fall off. Actually, there are point light source here, but actually this intensity fall off away from the given direction. Here, actually, I wanted to give the spotlight along that direction. Energy, actually, the light energy fall off as the light directions actually moving that directions. This is the spotlight. Also, that actually we can consider this kind of aerial light source here. So that's why it occupies. Before actually we assume that it's point light source, but here actually we used this kind of the aerial light. This aerial light, so that actually basically it occupies 2D area. It's like polygon or the disk, and that's why it actually generates soft shadow like this, right? So basically this aerial light like this, and also this is kind of the object, right? But this material, but at the location we are getting energy there, but we cannot receive the there, so right? So this is actually from here it's very bright, but here we can see if this light source more bigger like this, I can see I can receive the energy from there. I can receive the energy there, but not that much, right? I cannot receive the energy from there, right? So that's why it looks a little bit dark over there. So it gradually, the light energy actually gradually going down. Also here actually, as we actually at that location we can get all the energy from the light source, because of actually the light this kind of area looks like very dark, kind of fuzzy. That's why we call this a soft shadow, also the bright here. But in the end, they're actually representing this kind of aerial light actually takes a lot of time. So typically we are using back then we typically using this set of the point light source, but also we can approximate the aerial light with a lot of this point light. Also, there are some research how we can efficiently perform the aerial light source. Okay, so if I talked about this light source, now I'd like to move on to this actually reflector material. First of all, I'd like to talk about the simple one, ideal diffuse reflection. Basically, this kind of chalk is kind of the one example of the ideal diffuse reflector. So basically, if you look at the kind of blackboard or chalk, it actually reflects the energy uniformly over the hemisphere. What I mean by hemisphere is that I get back to the pen. Here, suppose that you actually incoming light direction here, then there's actually the material, right? But we can see we can actually consider the angle here. Actually, this is actually the 2D in the 2D space. We can just using this kind of this one angle here. The light this reflector can reflect the energy along that direction, right? Or that direction, or that direction, right? But here, as you can see, so the ideal diffuse reflector case actually it reflect the energy all possible direction as the same amount of energy. So that's why I use this one. If I receive the energy from here, it reflect the energy all possible directions in this 2D space, and then with the same amount of energy. So that's actually the one of the chalk actually having this kind of property. So that's why I'm changing back to the laser pointer. So that's why when I look, this is my if I put my eye here, I can see this one, since actually I can this reflect this chalk actually reflect the energy even that directions, right? If I'm locating there, also the chalk reflecting the energy from there to that direction. That's why I can see that chalk also the paper. It's the kind of one example of ideal diffuse reflector. So that's why the reflection is kind of view independent. Whatever direction your eye located, actually actually eye will get the same amount of energy. That's why it's kind of the view independent. Why we are having this kind of property? It's actually the chalk or the paper has a very rough surface at the microscopic level. So if we if we actually, the paper looks like flat, but if we zoom in this area, actually the paper has a lots of this fiber. So at the surface very rough like this, right? So you can reflect the photon all possible direction. That's why actually the chalk has this kind of property. Then the question, how can you actually explain, how can you represent this one with a simple equation? It turns out that it's actually Lambert's cosine law. Basically, Lambert cosine law tells us that reflected energy from a small surface area from illumination arriving from direction L. Basically, if you are getting the light energy from the L direction here, then this reflected energy, how much energy we can receive here, is proportional to the cosine of the angle between the L and also surface normal n here, the theta. So basically, this indicating then basically suppose that incoming light source has this intensity II. There could be the bright energy, a bright light source or a dark light source, which actually basically specified by this constant II. Then the reflected energy IR is actually view dependent, basically view independent. So basically across any view direction, this IR is basically computed by II multiplied by the cosine theta. So actually theta is here. Then you can see that actually this cosine term usually can be computed by this dot product between the two vector n and L. So this actually the reflected energy under the ideal diffusion reflector governed by this equation. And then this indicating that if the light energy actually from the above, then along to the orthogonally to the surface direction, the high energy actually reflected across all possible directions, since the theta is the 0 here, and then cosine 1 is 1, right? Then as you can see, as the light actually arriving at that location at a larger angle, theta here, then actually we are getting a more smaller energy. This also intuitive, this also align very well our observation, right? Basically on the mid noon, we are getting we can see that actually the reflected energy is actually very bright, but actually the error this near the sun, near the sunset. Actually, we are getting this the light direction in at a large angle, and then you can see the reflect energy. The basically environment looks a little bit dim, right? Then the question is that why actually the cosine term, right? So suppose that we actually arriving there the light direction with the theta here, but I assuming that we actually there are this kind of ray beam. Let's say this is actually the width here. Let's say this W, and then given this to W, and then this is theta, right? Then this theta, and then if we actually this the same width here, then this theta, and this also theta, right? This actually also theta, right? Then you can see that this light energy arrive with the W width, but this actually arriving this kind of more larger area, right? You can see the intuitively the light energy distribute more larger area as we got the more larger theta, right? You can see that it will be more getting less energy, right? Basically in terms of each the unit in terms of light energy receiving in this unit area, right? That's actually basically the basic density concept, right? We are getting the high density. It looks like more bright, less density. It looks more dim, right? Then the cosine term here is that if we are applying this W here, if you're applying the cosine theta, actually, let's say this width, this actually the width that we are receiving the ray beam here. Let's say this actually x. This is cosine theta is the x divided by W, right? And then light density here, right? Then basically if we assume that there are actually if we incoming this the total width actually W, then the light density here is that I divided by W, but this area actually same amount of energy, right? I, but divided by this area, the x, right? X is actually divided by cosine. So sorry about cosine theta over the W, right? Then if we summarize here, this is actually the cosine theta with the I divided W, right? You can see the cosine theta term here, right? So basically, given this the incoming light density, actually the light density actually reduced down to as a factor of cosine term. That's why actually we are getting this cosine term here. That's the actual physical explanation of the Lambert cosine law. If you actually basically my book actually explained this one carefully at the book. So if you want to know more detail, I recommend you to check out the paper, the book. And then the computer diffusion reflection, basically also the material actually has its own material property, which is actually given by this KD. So this actually the incoming light energy. This actual cosine term, and as KD is actually the material dependent. And material have a different reflecting this property. So which actually we just using this KD coefficient, and then this constant KD specify how much of the instant light energy diffused reflectively, right? This actually obviously KD is low, it looks more dim, right? And then if we change the light direction here, and then basically given this this P actually looks like this. You can see that actually the light actually looking at this object from here. This one light direction, maybe the light actually coming from here to there, right? You can see that, you can feel that, right? So in some cases, that this normal vector could be the negative. In other case, instant light actually may be blocked by the surface itself, and then obviously we don't want this kind. Obviously, there cannot be the negative energy, right? So we just make sure that diffusive reflection becomes 0. Also, now let's talk about the specular reflection. So specular reflector have this bright view dependent highlight. For example, this kind of mirror, or this kind of the glossy car finish, right? Also the metal, right? This is kind of the specular reflection. And at a microscopic level, the specular material reflecting the specular reflecting surface is very smooth, and then this surface also follow the Snell's law. You probably learned this Snell's law. So basically, the relationship between the angle of the incoming this is say this the incoming the light direction, and then this the given the incoming direction, if this mirror actually this incoming, this outgoing direction are right, the relation between the incoming reflected ray with the normal here, the surface normal will be given by this one, this actually Snell's law. Here Ni, No is actually constant, but the indices of the refraction in Korean is 굴절률. 물질마다 굴절률이 다르잖아요. 그죠? 물의 굴절률과 여러분 잘 아시잖아요. 우리 빛이 공기 중에서 물로 들어가면 꺾이잖아요. 그 스넬스도 똑같은 거고, 물과 공기의 그 굴절률이 다르잖아요. 그거죠. The Ni, No is indices of the refractions. Basically, if you're just assuming that if you're looking at the water, and then the light actually the bend from the air to the water, right? You see that, right? That's actually water and the air has different indices of refraction for the incoming and outgoing ray. Then typically in our daily life, this actually everything happen in the here air, right? At the case, the incoming, outgoing, the refraction index is same thing. It will be cancelled out. Then we don't need to care about the sign term. Then x outgoing angle same to incoming. This is actually a case of the mirror, right? Basically, in the mirror, if you're actually receiving the energy in the theta I, then outgoing energy also this direction also given by the theta O, which is same thing with the theta I. Also everything's incoming ray, surface normal, and the reflected ray all lie in the common plane. Obviously, in other cases, depending on the material, we might have this assumption, but typically in most of cases, we can have we can safely have this assumption. Then the question is, how can you compute this R vector, right? One simple solution, actually, this R vector can be computed like this. This actually can be computed by like this, the L vector negated like this. And then if we actually consider this one, this is actual L vector, this direction L vector, but this is actually the projected from the L to, basically this length, actually the projected length of the L vector onto the N. So basically we take the dot product, but there are two of them, 1 and 2. So that's why actually we have this term. Okay, so but actually so far we talked on ideal case, ideal, diffuse, ideal, the specular. Obviously a lot of cases there are non-ideal reflectors, right? So Snell's law that I talked before apply only to ideal one. So, but actually typically the surface cannot be the total perfect metal. So a lot of cases actually surface of has certain roughness, and also it actually reflects the energy here and there. So it called highlight. In other words, actually it spread out energy. So in other words, if you look at the kind of surface of the apple, then I don't know whether you have the apple, that kind of one. So suppose that you are giving this kind of incoming light energy, but actually it actually reflecting energy at a particular direction a lot. So at that direction it reflects energy a lot, but in other direction it reflects energy a little bit, right? Then if we look at this apple, suppose this is actually the reflection we have apple here. Then if you look at apple at that direction, this viewing direction, right? Then we are getting a lot of energy. So then it looks very bright. At that case, actually it actually has highlight. But if you look at the other direction, if you look at this apple at that direction, we're only getting this amount of energy. Then obviously apple looks dark. So we cannot see the kind of the highlight, right? So this is kind of the typical case. A lot of cases actually this have the non-ideal reflector. So we definitely need to have some sort of model that can actually represent this kind of appearance of the non-ideal reflector. So the empirical models try to simulate the appearance of this kind of effect without trying to capture of the physics of it. So obviously, if we can measure the BRDF, actually we can, then it'll be great. But we cannot have that kind of the complicated algorithm yet. So we actually, typical OpenGL actually had a very simple solution. We will talk about this one later on, but recent technology actually much more complicated. I cannot talk about the recent one, but if you're interested, you can check it out. Some of recent techniques like the GGX model, that kind of one, which actually also used in the recent games. Let's get back to laser pointer here. Okay, so that's it so far. I hope that by now you can understand how we can consider light. during the rendering model, we talked about the different types of light sources. Also, we talked about different terms we can actually represent this kind of the models, like the ambient term, the constant, diffuse. Actually, that's why I talked about the cosine term, the Lambertian cosine law. Also, I talked about ideal specular term. But actually, I didn't really talk about how we can actually, what are the empirical model for the this kind of non-ideal one. I will talk about later on. So that actually we can have by combining these terms somehow we can actually represent this kind of we can actually represent this kind of model with highlight the darkness and other ones. And that's it. These are the regular homework. Go over the next lecture slide, watching the 2 video paper and submit their summary paper every Monday. So I'm giving you this homework so that you can find your lecture topic, also the paper presentation, the paper. Also, I encourage you to submit 2 questions. You need to submit these questions so that I'd like to encourage you to think about it, lecture material, and then write down 2 times during the whole semester. Okay, that's it. And next time I'll actually put together everything together. I will talk about the Phong illumination model. Also, I will talk about some other topics like the shading. That's it. Thanks so much. Bye.